Just wanted to say a few words about how batteries work. We've been using batteries in electrical circuits. We've been using batteries to provide the electrical current, the electrical power for electrical circuits. We've seen how batteries distribute their electrical potential, their electrical current to circuit components. So where does this electrical power, electrical energy, electrical current come from in a battery? Firstly, just a broad perspective. In the natural world, we see all sorts of forms of energy. And we see energy changing from one form to another form, energy flowing from one form to another form. So light energy, sunlight, is turned into heat energy, keeps us warm. Motion energy is turned into electrical energy in an electrical generator. Light energy is turned into chemical energy in plants through photosynthesis. And also chemical energy is turned into electrical energy, and that's by a battery. So a battery is a device that converts one form of energy to another form of energy, chemical energy to electrical energy. And it's just one of many ways in which energy is changed from one form to another form. What is the nature of chemical energy? What really is chemical energy? Well, chemical energy is associated with the electrons of atoms and molecules. In some atoms, there's a greater affinity for electrons. In other atoms, there's a lesser affinity for electrons. Some atoms want to gain electrons. Other atoms are happier to lose electrons. And so when you compare atom with atom, molecule with molecule, a distinguishing feature between different types of atoms, different types of molecules, is their preference for gaining electrons versus their preference for losing electrons. If you remove electrons or add electrons to atoms, making ions, then there's an associated energy with that change in the number of electrons around an atom when you make an ion. That's chemical energy. That chemical energy is associated with the electrons of the atoms and molecules. So what is a battery? What's going on in a battery? A battery is converting chemical energy to electrical energy. It converts chemical energy to electrical energy through chemical reactions, actually through a pair of chemical reactions in which energy is released, and that energy is the energy that drives the electrical current around the circuit that's supplied by the battery. That's the energy that supplies the chemical energy, supplies the electrical energy to the circuit, supplies the electrical power to the circuit. It's the energy that gets dissipated in resistors, for example, gets dissipated to heat energy in resistors. The battery, a device for turning chemical energy associated with the electrons of the atoms and the configurations of the electrons of the atoms into electrical energy that can be carried around a circuit and dissipated in a circuit. Battery was invented by Volta in about 1800. The battery, Volta's battery, and batteries thereafter have several distinct components. They're sketched in this figure here. So one component is a metal over here on the left-hand side, a metal electrode. In this case, this metal electrode we're going to call the anode. We'll see why. A second electrode, a second metal. In this case of this battery, we're going to call this the cathode. We see why. And some sort of electrolyte. Here you see zinc sulfate and copper sulfate being the electrolytes. Now, in Volta's original battery, he had these three components, 2 electrodes and a electrolyte separating the 2 electrodes. He built his first battery out of a zinc electrode and a copper electrode, and between the zinc and the copper was cardboard soaked in brine. So his electrolyte was brine. You can make a very similar battery to Volta's battery simply with a nail, zinc nail, a copper penny, and a lemon. So the zinc nail is one of the electrodes, the copper penny is the other electrode, and then the lemon juice in the lemon, if you stick the nail into the lemon and the penny into the lemon, that provides the electrolyte. So all those batteries, Volta's first brine battery, the lemon battery that you can make at home, all this little bit more sophisticated and long-lasting battery here, they're all comprising a pair of electrodes of different metals. We call an anode and a cathode, and then some sort of electrolyte. So what is happening in the battery? Where does that electrical energy come from? Where does the electrical potential between the 2 electrodes that drive the electrical current through an electrical circuit, where does that come from? Well, in all of those batteries, the brine battery, the lemon battery, and this battery that I pictured here, is chemical reactions that drive the electrical current around the electrical circuit. And it's actually a pair. Batteries involve a pair of chemical reactions. So in this particular battery, I'm going to write down the 2 reactions that are occurring. One reaction is on the left-hand side at the zinc electrode and involves the zinc. And the other reaction is on the right-hand side at the copper electrode and involves the copper. So I'm going to write these 2 down, and then I'm going to discuss them. So upstairs here and downstairs here, these are the 2 reactions. The reaction involving the zinc, this upper reaction, is happening at the zinc electrode over here on the left. And the reaction involving the copper, this reaction here, this is happening at the copper electrode over here on the right. So both of these reactions are happening simultaneously. And overall, these reactions release chemical energy. We said that chemical energy is associated with the configuration of the electrons in the atom or the ion. These are changing the configuration of the electrons and atoms in the ion, and therefore they're changing the chemical energy, and specifically they're releasing chemical energy, which provides the electrical energy for the electrical circuit to power the resistor, to allow the resistor to dissipate electrical energy as thermal energy, heat energy. So the first reaction is involving a zinc atom that's on the left-hand side. This is a neutral zinc atom. And from the zinc atom is liberated 2 electrons. And if we liberate 2 electrons from the zinc atom, that's going to be leaving a positively charged zinc ion. And that's what's indicated here. So this is liberating electrons at the left-hand side electrode. And that liberation of electrons, supposing we hadn't completed the circuit, will cause electrons to build up on that particular electrode. So I've indicated a few negative charges building up here. The second reaction, that's involving the copper. And if you look over here on the left-hand side of the reaction, this is actually the copper ions in the copper sulfate solution in the region of the copper electrode. So these copper ions are positively charged. They are ions, they're not neutral. And these copper ions are picking up electrons from the copper electrode here. So this copper ion picks up 2 electrons and becomes a copper atom, a neutral copper atom, and part of the electrode gets deposited on the electrode. So that's the second reaction that's happening over here. And that causes this electrode, if the circuit's not yet complete, we basically added a copper ion to the electrode, which is picked up to the electrons. Because we added a positive copper ion to the electrode, this electrode is now becoming positively charged. And so it's via these 2 reactions, the zinc reaction on the left that's liberating electrons, and the copper ion reaction on the right, it's kind of gobbling up electrons, that this electrode on the left-hand side becomes negatively charged. This electrode on the right-hand side becomes positively charged. And this causes an electrical potential between the 2 electrodes. And that electrical potential, its value is determined by the amount of energies that are released or needed when electrons are removed from zinc or copper, or added to zinc and copper. And actually, it's 1.1 volts of electrical potential that arise between the 2 electrodes based on the energetics of these 2 reactions that are going on. Now, when we hook up the circuit, and the circuit involves a wire in red here that runs from the anode to the cathode. The anode is just the name we call the negative electrode. The cathode is just the name we call the positive electrode. So we're making a circuit here with this wire in red. There might be a resistor in there in which we're going to dissipate some energy, dissipate some power. Actually, there's another part in this battery of the circuit. There's this part here, which is called an iron path. It might be some damp paper or some damp cloth that's just draped between these 2 vessels of the zinc sulfate and the copper sulfate. But it's a path through which ions can flow, in particular the sulfate ions. The negative sulfate ions will flow from the right-hand side to the left-hand side. You can see here it's really completing a circuit. Negative charge in the form of electrons is flowing from the zinc electrode over here to the copper electrode. So negative charge is flowing in this direction from left to right as electrons, but simultaneously, otherwise we would build up charges on the left and right, net charges on the left and right. Simultaneously, sulfate ions are flowing from the right-hand side back to the left-hand side, from the copper sulfate to the zinc sulfate over here. As this battery runs, we're liberating electrons on the left-hand side. We're recapturing those electrons on the right-hand side, and zinc sulfate ions are flowing from the left, from the right to the left. There's these 2 reactions going on. These 2 reactions are creating, because of their energetics, because of the different energies released or gained by adding or removing electrons for zinc and copper, they're causing a 1.1 volt potential difference between the anode and the cathode. And that's the potential hill that causes the electrons to flow, causes the current to flow between the 2 electrodes. So this is how a battery works. This is how the brine battery with the zinc and the copper electrodes that Volta developed works. The exact reactions are a little different. This is how the lemon battery with a zinc electrode and a copper electrode works. Again, the exact reactions are different, but it's basically how it works. It's how all sorts of batteries work. to modern day lithium batteries, that nickel lithium batteries that are in, for example, electronic devices that we walk around with, our cell phones, our computers, our iPads, but also for things like cars. Gasoline cars require a battery to start them, and electric cars require a battery to move. And so batteries have become incredibly important in our everyday lives. And this is how a battery works, how it turns chemical energy into electrical energy. I wanted to make a last remark about why do we get 1.1 volts with the Volta battery, the battery with a zinc and copper electrodes and either a brine or a lemon juice electrolyte. Why 1.1 volts? And also I wanted to make a remark about why there's an internal resistance for a Volta battery with the zinc and copper electrodes and brine electrolyte or any other battery. To understand these two things, let's just imagine the chemical reactions that are occurring at the two electrodes, how the charges build up on the two electrodes, how the voltage between the two electrodes builds up, and what drawing current from the two electrodes does. So I've got a picture here of the two electrodes in a zinc copper brine battery or a zinc copper lemon juice battery. On the left-hand zinc electrode, the zinc is being ionized. Zinc atoms are turning into positive zinc ions and releasing electrons. On the right-hand electrode, the copper ions in the solution are being atomized. So they may be made neutral by taking two electrons from the copper electrode. So let's imagine the very first pair of reactions on the left and right of the zinc and the copper. So this is the very first zinc atom that becomes an ion, the very first copper ion that becomes an atom. If we imagine that very first reaction, that's going to produce a pair of electrons. I'll just write that as a negative charge on this electrode over here on the left. It's going to create a positive charge on this electrode over here on the right, because a copper ion that was positive is becoming part of the electrode. Now, to put the positive and negative charges on the two electrodes, we had to do essentially no work, because the potentials were kind of at equal potentials on the two electrodes. There was no potential hill between the two electrodes. But now we've actually created a little potential hill between the two electrodes. We got negative charge over here on the left. We got positive charge over here on the right. There's a potential hill. It's a very small one because we just got a couple of units of electronic charge on both electrons. Very small potential hill, but there is a potential hill between the two electrodes. As the next reaction goes ahead, we get more negative charge on the zinc, more positive charge on the copper, and the next reaction goes ahead. We start to build up the charges on the left-hand and right-hand electrodes. And as we add more and more electrons on the zinc electrode, add more and more positive charge on the copper electrode, that potential hill between the two electrodes is going to climb and climb and climb. And at some point, as this potential hill is climbing, that potential hill becomes too high for the reactions to occur anymore. It's too high for the electrons to be put on the zinc electrode. It's too high for the copper ions to get onto the copper electrode. That means that the electrons, of course, are produced in this reaction are repelled by the negative charge on the zinc electrode, and that brings to a halt the reaction. It's just not energetically favorable anymore. And likewise for the copper ions, as the copper electrode becomes more and more positive, this reaction becomes at some point not favorable, not energetically favorable. It costs too much energy to put the copper ion, the positive copper ion, added to the positive electrode. At that point, that's the point when you establish this 1.1 volts between the two electrodes. That potential hill between the two electrodes is 1.1 volts. It's when you've shut off the two reactions that are depositing positive negative charge on the two electrodes, and that 1.1 volts is determined by the energetics of the two reactions, how much energy is released overall in the ionization of the zinc and the atomization of the copper. Now let's connect this battery to a circuit. So let's draw a circuit. I'll just draw a simple circuit, imagining a wire connecting the two electrodes. In reality, this is a circuit with resistors and other components. At this point, if we connect these two electrodes to into the circuit and make a complete circuit, then that allows electrons to flow off the negatively charged zinc anode towards and onto the positively charged copper electrode. That gives more room, more space, more electrical space for the zinc reaction to start occurring again and repopulate the zinc electrode with negative charges. So we'll get some more negative charges over here. It gives more electrical space for the copper reaction to go ahead and populate the copper electrode with more positive charges from the copper ion. So we start, when we're drawing a current between the two electrodes, a current that's flowing through the electrical circuit, then we're constantly replenishing the electrodes on the left and right with electrons or positive charges. And so that's how the current is maintained. We don't just draw down the charge on the two electrodes. Rather, we maintain the current on the two electrodes. However, that's fine for a small current. If we draw a small current, a relatively small number of electrons travel from the zinc to the copper each second, say, that a rate of reaction, so a rate of the zinc reaction, rate of the copper reaction that's supplying the charges is sufficiently large to replace the charges that flow through the circuit. But if we try and draw a large current, a high current between the two electrodes, our rate of reactions, our zinc reaction and copper reaction, they actually can't keep up. And they can't keep up. And so we do start to deplete the charges on the zinc negative electrode and the copper positive electrode. If we deplete the number of charges on the two electrodes, that is depleting the electrical potential hill between the two electrodes. That is, if we draw a large current, we see a smaller voltage. That is the effect of the internal resistance. So the internal resistance in a battery, in this zinc copper brine battery, is not a resistor, a component inside the battery. It's a model of how, if we try and draw a large current from the battery, our reactions, chemical reactions that supply the charge won't keep up. If we are just drawing a small current from the battery, our chemical reactions that supply the electrons and positive charges, they can keep up. So it's a model of that process. Well, that's the battery. That's why you get 1.1 volts for this particular battery. It's why you have an internal resistance for batteries. Well, that's the battery. It was an incredibly ingenious invention by Volta. The idea of putting together two different metals and zinc and copper separated by a piece of cardboard or a piece of cloth that's soaked in brine. Just seems amazing, remarkable to me. That invention of the battery obviously has incredible practical applications in our modern lives. It also had incredible scientific applications, both in physics and chemistry. It opened the door to understanding that chemical reactions are electrical